Um, Today's topic is all about how we go about architecting and building software systems capable of extreme transaction processing. And by that I mean, what you see on the slide here. So hundreds of thousands of transactions a second, tens of millions of entities in the working set. So we're not just talking about high throughput systems here, but also non-trivial amounts of data. Zero data loss in the face of failures, and we want to do this all in such a way that we can scale the system linearly with the business while meeting our availability SLAs. We want to do all this in the face of hard constraints on consistency and reliability. So trading systems, large-scale international e-commerce, order processing systems, and things like that. Maybe most importantly of all, we want our systems to be agile, and by that I mean they should be easy to maintain and scale as the business changes and evolves. I really want to emphasize too that none of this is theoretical. These are requirements for real-world systems up and running in production today. So this isn't an academic exercise. Before we can talk too much about what it takes to build our extreme systems, let's review some architectures that you've probably seen in the wild, consider some problems we might run into in trying to get them to scale to meet our needs. So first up is our traditional application architecture, and this probably looks familiar to a lot of folks. So we've got requests coming in via HTTP with no real routing smarts, big old monolithic relational database behind it all, backed by a disk. The application tier is probably using some kind of ORM to gloss over the fact that we need to speak SQL in our Java code, and we probably need to do some level of explicit manual transaction management. Typically, when we run into performance problems in a system like this, we react by scaling the application tier horizontally. Maybe that's more request processing threads or new instances of the application, something like that. Either way, all that does is put more load on that poor old database at the back. And if our SLAs allow it, maybe we can periodically, bring the system down, throw more RAM at the database, or CPUs, or disk, or whatever you need as the business grows. And that'll work for a while, but eventually it all comes grinding to a halt. Whether it's a bunch of contention from tens of thousands of clients or some runaway query that soaks up enough resources to prevent other threads from making progress in a reasonable amount of time. Inevitably, you end up with a team of people just to keep the database limping along. You don't really ever get to solving that scalability problem. And this is exacerbated too by the way most HTTP server frameworks tend to operate. There's typically a pool of threads dedicated to handling requests, and unless the framework has good async support, you need to block the request thread waiting for the backend to respond to you. And on top of that, if our durability requirements demand synchronous commits, then our request threads are blocked until the database successfully syncs changes to a transaction log on disk. So at a minimum, our request threads are sort of throttled by the disk on the database. And that's obviously not a great situation to be in. Some database backends let you configure more relaxed constraints to improve performance there, but of course, the trade-off is an increased risk of data loss, and again, at the end of the day, you're not really solving the scaling problem. So the monolithic relational database doesn't scale with the size of our data, and it doesn't scale to handle increased volume as we pile on more throughput. It's not hard to see why this architecture might not scale with our business. And so next, we might hear that this whole in-memory thing is cool, and maybe we want to leverage some sort of NoSQL in-memory database. And it's still a monolith, but we stack it with a pile of memory and keep it all resident. And in order to offer some level of durability in the face of machine failure or something like that, we also replicate the database. And here, maybe performance improves, but a lot of the same scaling problems are still present. So everything hinges on that in-memory database being fast. But as we scale up our application tier, we introduce more concurrent requests to our backend. That probably means a lot of contention if we happen to be write-heavy, because we're taking locks or retrying CAS operations or whatever. So you end up playing the same game here. You might be able to squeeze a little bit more performance overall, and you can still limp along by scaling vertically for a little while, but sooner or later you're going to hit a wall. So now we're finally starting to get away from designs built around monolithic backends and starting to think a little bit more about sharding our data. Again, this probably looks familiar to a lot of folks, and it's a big improvement with respect to our earlier scaling issues. In this architecture, we shard our application data tiers by some key. So maybe it's by customer or ticker symbol, product, whatever, it doesn't really matter. Depends on the business. Whatever that key represents, we then route inbound messages to the appropriate sharded application instance based on that key. Each instance of the application tier is backed by its own private in-memory replicated data store. So even though we're not immune to contention within the scope of a single shard, we don't add additional contention by adding new shards. So since each application shard has its own data store, the scaling problems we observe when dealing with our monoliths go away. If we need to scale, we add a new shard, update our routing tier, and we're pretty much done. Maybe there's a little migration that needs to happen as well. So now we've got a scalable architecture, but there's still some room for improvement on the performance side before we can really think about hitting our extreme performance numbers. So let's take a look at what that takes in some more detail. So why are we still slow and complex? You can see some latency and throughput numbers there that you might expect with a design like this. The first problem on the performance front is the fact that we need to go out of process to access our data store. So despite the data tier being in memory, we're still separated from it by a network hop. And we've still got the ORM problem in that we can't really talk directly to that memory without a few layers of abstraction. So perhaps our in-memory database only exposes a REST API or some sort of binary JSON-like protocol over a TCP socket or whatever. Anyway, as a result, there's still a lot of overhead there to deal with, just communicating with that database backend. But all we really want to do is sort of, update some fields in memory. Next is the fact that the stabilization of writes needs to occur synchronously. We can't just assume that our write was successful and move on to do other work. We still need to wait for an act from the data store to let us know that everything completed as expected. So we've still got that problem like tying up threads and all that sort of thing. So you can see, we've got latency in the vicinity of hundreds of milliseconds. Throughput with a single thread would mean that we can only do 10 transactions a second, which is obviously not great. So our application logic is still a little bit complex due to the added complexity. It's also complicated by the added concurrency. It's also complicated by manual transaction management in our business logic to a certain degree. And as I mentioned before, we've still got to translate from our programming language's representation of our data to a representation that can be understood by a data store. So whatever is the in-memory data store's equivalent of SQL or whatever. Anyway, the point is all of this can be impactful on your performance and agility. So what can we do to improve that situation? So first of all, we take our in-memory data store and basically get rid of it and move the application state in process. So by doing so, we eliminate the network hop and we keep our state as close as possible to our business logic, which tends to make our CPU caches very happy. Next, we pipeline transactions, meaning we do things like decouple replication from our business logic. While we're replicating and stabilizing the previous transaction, we've already started running our business logic on the next transaction. An inbound message implies the beginning of a transaction. Only once a transaction is replicated and stabilized, we then send the outbound messages. So this point here about all interactions with the outside world going via messaging is critical for this reason. The outbound messages are effectively indicating to other systems that a transaction has been stabilized or committed. Hopefully that makes sense. To simplify the lives of application developers, business logic runs single-threaded. Modern commodity server CPUs are really, really fast at 2 or 3 gigahertz minimum. If we make good use of our CPUs, a single CPU can typically meet the performance goals we outlined at the beginning of the presentation. Finally, we use constructs native to our programming language to model and manipulate our application state, where we don't want to be manipulating Java objects only to eventually convert them into SQL or JSON and send them to some external data store. We want our Java objects to be the state. So our Java objects are the state. So taking all that into account, you might be able to imagine a system where an inbound message is routed to an instance of our application and the business logic runs to process it. Since the business logic runs single-threaded, we can update objects in memory without any funny business with locks or tricky CAS operations, or any lock-free algorithms or anything like that. The business logic completes, the stabilization process begins to kick off, so we're replicating our state changes. Meanwhile, a new inbound message arrives and our business logic starts processing it while we're waiting for the previous transaction to stabilize. So by bringing our state to our business logic, eliminating the overhead typically involved in communicating with an external data store, and pipelining transaction processing, we can really unlock the potential of in-memory computing in a way that scales by keeping our business logic single-threaded and tackling transaction management implicitly. We keep our implementation simple. And this is sort of the promise of the X platform. We provide all the code infrastructure that makes all this stuff possible. Let us take care of the pipelining, the replication madness, and the transactional semantics. All you should really need to worry about as a developer is writing that business logic. And since it's single-threaded, X applications are easy to build and maintain. So what are the performance characteristics of an architecture like this? So straight up we can see a few orders of magnitude improvement. In our earlier architecture where the data store was kept out of process, we were talking hundreds of milliseconds. Now we're looking at hundreds of microseconds and hundreds of thousands of transactions per second with the strategies employed by the X platform. Excuse me. If latency isn't too much of a concern, maybe you can stop here and be happy, but there's still some room for improvement. So as an example, you might want to avoid buffer copies when you're moving data between the network and your business logic. Copying data takes time, so not much more to it than that. But the really obvious one with Java is the garbage collector. So anytime the GC runs, you could probably expect millisecond-long pauses. It's not unusual for a GC to take 10 milliseconds. So if you want reliable latencies, you need to avoid generating garbage. That typically means pre-allocating, pooling, recycling objects. By doing so, you can really start to push down into the vicinity of tens of microseconds and do so in a way that you don't get quite so much jitter. Again, the X platform supports this stuff out of the box. So that just about wraps things up. Leveraging this architecture, you can build systems that really unlock the promise of in-memory computing, so you get awesome performance without sacrificing reliability, scalability, or simplicity of implementation. The X platform, in turn, makes it easy for engineering teams to build systems around an architecture like that. So without getting too far into the weeds, on this side, you can see some of the products that make up the X platform suite. If you're looking for raw message processing power, streaming capabilities, things like that, probably want to look at Talon. It offers full support for building your own pipeline transactional business logic on top of a local in-memory replicated data store, just like what we covered in this presentation. On the other hand, if you're looking more at microservices, check out Eagle, which pairs a HTTP server with Talon. So under the hood, you're still using the same goodness. Then down the bottom here, we've got Robin and Lumino, which are basically our deployment monitoring command and control tooling. So once you've deployed all these things, you want to keep an eye on them and maintain them and all that sort of thing. And Lumino and Robin let you do that. But I won't go too much into them just now. But that's pretty much it from me.